All right, let's get right into it. You've written some amazing code in a language like, say, Python or C++. But here's the thing. How does your computer, which really only understands ones and zeros, have any clue what you're telling it to do? Well, that's exactly what we're going to break down.
I mean, this is really the core problem at the heart of all programming, isn't it? We, as developers, we write our instructions in these high-level languages that are pretty readable to us, but to the computer's processor, it's total gibberish. There's this huge communication gap that we absolutely have to bridge.
So to solve this problem, you need a translator. And in the programming world, this job is handled by two very different kinds of programs. We've got compilers and we've got interpreters. They both get the same job done, but oh man, their methods are worlds apart.
First up, let's meet the meticulous planner of the programming universe, the compiler. Its whole philosophy is built around doing all the hard work up front.
The best way to think about a compiler is to imagine it's a book translator. They take an entire novel, say War and Peace, read it from cover to cover, and then translate the whole thing into a brand new language. Only after they've finished that complete, final, translated book do they actually hand it over to you to read.
And this whole process is really an all-or-nothing deal. The compiler scans everything first, checking the entire program for any errors. If it all checks out, then it translates the whole thing into machine code and packages it up nice and neat into what's called an executable file. That's a standalone program you can just run whenever you want.
So doing all this work up front has some major trade-offs. The big payoff? Speed. Because the translation is already done, the final program runs incredibly fast. But here's the downside. You won't know if you made a simple typo on line 5 until the compiler has already tried to read all 5,000 lines of your code. It just gives you one big list of all the errors at the very end.
Okay, now for our second approach, the interpreter. This one has a completely different mindset. It's our spontaneous, on-the-fly translator.
So if the compiler is a book translator, the interpreter is like having a live, simultaneous translator at a big conference. They listen to one sentence, translate it right then and there, and then wait for the next one. It's all happening in real time, a continuous back-and-forth process.
So yeah, it's a purely step-by-step method. The interpreter doesn't care what's on line 100. It reads line 1, translates it, the CPU runs it, and only then does it even think about moving on to line 2. There's no waiting for the whole thing to finish, and no separate file is ever created.
Now the huge advantage here is that you get immediate feedback. If you have an error on line 5, bam! The program just stops right there and tells you exactly where you messed up. That can make finding and fixing bugs way faster. But this constant process of translate then execute, line by line, well, it generally means the program's overall runtime is going to be slower than a precompiled one.
All right, we've met our two translators. Now, let's really put them side by side. You know, a little head-to-head comparison to sharpen our understanding of what makes them so different.
Looking at this table, you can really see the clear trade-offs, can't you? The compiler is playing the long game. It bets on performance by doing all the work up front. That gets you a fast final product but makes you wait for error reports. The interpreter, on the other hand, bets on flexibility and making the developer's life easier, giving you that instant error feedback, but at the cost of runtime speed. So, with these very different philosophies, which popular programming languages end up choosing which path? Well, the answer actually tells you a lot about what a language was designed to do in the first place. So over on Team Compiler, you see the heavy hitters like C++ and Go. These are languages famous for performance-critical stuff like video games or major system infrastructure. Then over on Team Interpreter, you've got languages like Python, JavaScript, and Ruby. And these are celebrated for getting things built quickly, for web scripting, for data analysis, situations where your development speed is often more important than raw execution speed.
At the end of the day, it really comes back to that core analogy, doesn't it? Neither of these methods is just plain better than the other. They are simply different tools for different kinds of jobs. When you choose a programming language, you're often implicitly choosing the translation philosophy that best fits your project. Do you need raw performance or do you need flexibility?
You know, this choice between upfront optimization and dynamic, on-the-fly agility is still a huge theme in software development today. In fact, a lot of modern languages, like Java, even use a hybrid approach to try and get the best of both worlds. It really leaves us with a fascinating question. As our software gets more and more complex, will we favor the perfect pre-translated master plan or the agile on-the-fly interpretation? The answer to that is probably going to define the next generation of software.